Good evening, guys. I have discussion A for you. It's discussing how neuroscience breakthroughs haven't led to better treatments. So that's what we're discussing for A. So please join me in tonight's discussion A. Neuroscience breakthroughs. Despite decades of brain research, conditions like Alzheimer's and depression still lack consistently effective treatments. University of Pennsylvania professor Nicole Rust explores this issue in her book Exclusive Cures. She emphasizes that while the brain's adaptability is its strength, it also makes it vulnerable to disorders, something not easily addressed by simple cause and effect. Rust argues that researchers need to adopt a systems based approach, viewing the brain's viewing the brain as a dynamic feedback rich network rather than a linear system. She draws comparisons to paradigm shifts in ecology and cell biology, and is helpful. New technologies will support this broader perspective. Russ's career and shift focus. Writing a book inspired Rust to pivot her research from memory to mood. She received the Simons Foundation Pivot Fellowship and will collaborate with Princeton, Neuroscience, Yale, NIV to deeper her understanding of mood regulation. Parallel concerns and pharmacological risks. A linked study from the University of Nottingham highlights that long-term use of strong anticoagulant drugs commonly prescribed for bladder control conditions, Parkinson's, and depression is associated with a nearly 50% increased risk of dementia in older adults. The Alzheimer's Society underscores these findings and warns that even short-term use in frail older adults could impact cognition. Let me know if you'd like a deeper dive into any of these themes, like the systems thinking model Rust is advocating, or the mechanisms behind anticoagulants, drugs, risks. A systems based approach in neuroscience brings several compelling advantages, especially for complex conditions like Alzheimer's, Parkinson's, or mood disorders that don't respond well to linear single target models. Here's how this perspective makes a difference. Embraces the brain, embraces the brain's complexity. The brain isn't a static uh, structure. It's an adaptive, self-organizing network. A systems model captures the feedback loops, emergent behaviors, and interconnected pathways that shape how we think, feel, and function. This perspective helps explain why small changes in one region, like inflammation or neurotransmitter shifts, can ripple across the entire system. 2. Shifts from symptom silencing to root cause insights. Traditional models often isolate a single molecule or brain region, like targeting dopamine in depression. A systems lens looks upstream and downstream. Why is dopamine uh, dysregulated? What other systems are compensating or collapsing? 3. Guides precision therapies. By mapping networks instead of isolated points, researchers can identify multi target interventions that adjust the system gently rather than uh, harming one receptor. Reduces unintended consequences. Single target single target drugs often cause side effects by disrupting their essential processes, e.g., anticoagulants, increasing dementia risks. Systems thinking builds resilience by aiming for balance, not brute force. Change. 5. Fosters interdisciplinary innovation. It opens a door using tools from ecology, data, science, engineering, and complexity theory, marrying Nicole Russ's comparison to paradigm shifts in cell biology. These cross pollinations could enable better diagnostic, adaptive therapies, and even mood regulating technologies. Given your background, I imagine this holistic mindset resonates, especially when thinking about how precision medicine or multimodal care strategies might evolve. Um, would you like to dig deeper into how this model could influence dementia care or pharmacologic therapies, frameworks? Absolutely. There are some standout examples of system based neuroscience research that might spark your interest, especially given your focus on precision care, complex aging conditions, and innovation in health systems. Okay, Human Connect Project, or HCP. This large scale NIH initiative maps structural and functional connections across the entire brain, treating cognition and behavior as network level phenomenon. It has revealed how disruptions in hub regions like the default mode network are implicated in disorders such as Alzheimer's and schizophrenia. Instead of targeting individual regions, HCP style models help identify how dysfunctions propagates across systems, mirroring your own emphasis on systematic innovation frameworks. To Allen Brain Access and Cell Types database. Rather than isolating one brain region or pathway, This project catalogs cell types, gene expressions, patterns, and systematic synaptic connections across species. It enables multi scalar modeling, linking molecular dynamics to neural circuitry and behavioral outputs. Uh, the cross species perspective also enhances transitional work in neurodegenerative conditions like Parkinson's and ALS. 3. Mood disorders as network dysfunctions. Princeton and Penn researchers, including Yale, NIV, who Rust will collaborate with, model depression and anxiety as not as chemical imbalances, but as circuit level dysregulation of reward and validation systems. These models incorporate computational psychiatric psychiatry and Bayesian's influence to understand mal maldi mal maladaptive predictions, effective inertia, and treatment responses to variability. System pharmacological and polypharmacy modeling. Stanford's para uh, Stanford's para param param GKB and similar efforts to map gene drug decrease interactions across biological systems, especially in aging populations. Systems pharmacologically helps predict cognitive uh, burdens of multiple interacting medications like anticoagulants based on network uh, para, pertum fashion mapping based on network uh, pertum fashion. This aligns closely with your interest in minimizing cognitive footprints, and rethinking polypharmacy risks. Neuroinflammation as a systems level process. In Alzheimer's research, microglia activation and cytokine feedback loops are increasingly framed not just as local pathology but as systematic immune brain crosstalk. Studies at institutions like UCSF are modeling how peripheral inflammation, or BBB, parametabability, and Janelle priming feed into feedback rich loops that exacerbates TAU and AB toxicity. These systems based initiatives are helping refine how we conceptualize, diagnose, and treat brain disorders, not as isolated multifunctions, but as breakdown in finely tuned biological networks. If one of these examples especially resonates, I'd be glad to explore how it could reshape current dementia care strategies or end of life planning models. Especially since systems based neuroscience thrives on methodological diversity to capture the brain's complexity across scales. Here's a breakdown of the most commonly used approaches. Network modeling and graph theory. Researchers map brain regions as models and their interactions as edges, creating connections that reveal how information flows. Matrix like centrally molecule T and small worldness helps identify hubs and bottlenecks in disorders like Alzheimer's and schizophrenia. Two, multi-scale imaging techniques. fMRI, and DTI capture large-scale brain activity and structural connectivity. 2. Photon microscopy and light sheet imaging allow real-time observation of neural circuits in animal models. These tools support microscopic analysis, bridging cellular and system levels. Let's see. Computational modeling and simulation. Dynamical systems models simulate how neural populations interact over time. Bayesian models, reinforcements, learning frameworks like those used by Yale, NIV help explain mood and decision making as emergent properties of network dynamics. Optogenetics and chemogenetics. These techniques let researchers precisely control specific regions within circuits using light or designer drugs. They're crucial for testing causal relationships in feedback-rich systems. Okay, transcriptions and cellular type mapping. Single-cell RNA sequencing and spatial transcriptomics via the alien brain access reveal how gene expression patterns shape circuit function. This supports bottom-up systems modeling from molecular to behavioral levels. Systems pharmacologically and polypharmacy modeling. Tools like PharmaGKB integrate drug gene disease networks to predict how medications interact across systems, especially relevant for aging populations where cognitive footprints of polypharmacy are a concern. Machine learning, AI integration. Deep learning models analyze massive data sets from the human connexome project direct patterns invisible to traditional stats. These models are increasingly used to predict disease progression or treatment responses. Okay, guys, that is A for you. I will be back on with B shortly. Give me a bit for B, please, and I'll be back on with you. For now, Gator Wellness, take care, folks.